copied that equation down over here. So it's copper plus 2 electrons yields copper. And the reduction potential this last bullet point, I suggested when I put the slide up that you're not going to like this. The reason is this, because we learned back when we talked about Hess's law that when you have a chemical equation with a delta H, if you need to multiply through by a 2, for instance, then you'd have to double its delta H. If twice as much reacts, you're going to get twice the amount of energy out or have to put into it. However, when we're dealing with reduction potential, that sign right there, the naught sign, does not mean the same as the naught sign with delta H. The naught sign here means that your solutions are at a concentration of 1 molarity. And because of that, if you have to multiply this through by 2, this is implied that it's, the solutions are at a concentration of 1 molarity. So it wouldn't change. It still has the same concentration. So no matter what the ratio of the reactants are to one another, or what ratio the products get made in, these are not affected by coefficients. So this is a third different thing that we've learned about how when you have to manipulate equation. With Hess's law in thermochemistry, when you multiply this thing through, you multiply the delta H by the same factor. When we learned about equilibrium constant, when you multiply it through by a multiple, then the K value gets raised to that power. Remember that? Like if you multiply through by 2, then you square the K value. Now, with reduction potentials or oxidation potentials, when you multiply by 2, you do nothing to that number. You do nothing at all. So yeah, that's a little bit different. And that's what I'm saying here in this last bullet point. Okay, now the next 2 slides are going to take us through all the things that we need to know about describing a cell. There's 5 things. And the first, very simple, we need a balanced equation, and you'll have to come up with a cell potential from the table. The next component in a description of a cell, you have to, this is simple, show the direction of electron flow. When I draw a cell, I always do it the same way. I'll put the anode on the left, the electron's leaving the anode, and the cathode on the right. So the direction of electron flow is always from left to right. That's the way I do it. You can do it however you want. You can certainly put the anode on the right and have the electron flow going to the left. Have at it. Number 3, the problem almost always will ask you to identify the anode and the cathode. Now, I know the book confused a lot of you. One of you asked me before class, but I know other people were kind of scratching their heads over. The thing that gets oxidized in a reaction is known as the reducing agent. Remember the picture in the book? They labeled the anode, but then it said reducing agent. You're like, huh? I thought that the anode had the thing that got oxidized. Yes, the thing that gets oxidized is the reducing agent. Now, I know that's confusing, but you'll see that as we continue to do electrochem, how you can kind of justify why you would call the thing that gets oxidized the reducing agent. And on the other side of it, the thing that gets reduced is the oxidizing agent. So we'll have to label the anode and cathode. And then number 4 gets a little tricky. You have to identify the electrode that you're using in the anode and the cathode, the electrode. Here's what I mean by, I'll come right back to the slide. But yeah, on Friday I showed several duplicate slides that had this picture in it. And you'll notice that every time we'll draw a picture of a cell, you're going to have a metal plate in the anode and a metal plate in the cathode. And when I showed you that demonstration back there of the reaction between iron and copper, I had a nail as my electrode for the iron and a copper sheet for my electrode for the copper. You always have that electrode. The electrodes are the vehicle for getting the electrons from one solution to the other. I mean, it goes through a wire, but the wire must be attached to an electrode, which is in the solution. So you always will have to label the electrodes, what they are. Now, when your half reaction has, when that compartment has a metal as a reactant or a product, that's a no-brainer because you'll use that metal. That's why I used the iron nail in the iron and the copper sheet in the copper. That was a pretty simple thing. So if the half reaction contains a metal, use that metal as the electrode. I'll just uncover the rest of this too. It's pretty common to not have a metal in your half reaction. And in that case, we'll have to use some inert conductor. And the best choice is platinum. Platinum is a good choice for two reasons. Number one, it's a really good conductor of current. It's got a low resistance, man. You can really move electrons through it. Second thing is, it doesn't react with hardly anything. So a non-reactive thing. You don't want to put something into your solution that's going to be reacting too if you're trying to look at other things in there that are reacting. So the fact that platinum is pretty inert makes it good. The drawback, it's a huge drawback. We can't afford it. You can't use platinum for on a high school chemistry budget. So we had to come up with poor man's platinum. What could we use instead of platinum? Well, we have a very good option. Just a simple graphite rod. These things conduct current. The graphite is it's pure carbon with a lot of double bonds in there. And the double bonding and the layering network in graphite makes it a pretty good conductor. And graphite is fairly inert as well. So yeah, graphite, the same stuff that you use in pencil leads. You could take a pencil lead out and use that for an electrode. That would work. So yeah, may I? Oh, isn't that nice? So that's our graphite. Normally, I will take the graphite if you need a conductor or an electrode, and I'll say, well, here's your platinum. So we can pretend that we have platinum. It works just like it, but yeah. Do you know what platinum looks like? Would you know if you had it? It's silver in color, and it's very dense. It's more dense than gold. The density of gold is like 20 grams per centimeter cubed. It's very dense. Pure gold is. And I think platinum is even more so. Yeah, platinum is 21 grams per centimeter cubed. You would know it. It's very heavy. Like if a guy has a ring made of platinum, they know it's on their hand. It's heavy. Okay. Now, the last thing is, this is going to be strange as well. You have not seen this yet. Line notation. Line notation is a way that we express an electrochemical reaction. This is specific to electrochemistry. You won't see line notation, I don't think, anywhere else. Now, what I have written up there, that's a chemical equation. That's not line notation. You're familiar with that. We can take this equation and express it like this. This is what we consider line notation. That's different. Make sure you get your charges in the right place. So what we do when we write numbers in line notation, or not write numbers, but write chemical equations, the thing that gets oxidized is always written first. So really what the line notation does is it breaks the chemical equation up into half reactions. The double line separates the anode from the cathode. Anode is always written first, always. So this shows us that iron is oxidizing into iron plus 2. That's what we have in the reaction. And then in the cathode, we have copper plus 2, reducing to copper. So it's always written with the anode on the left, 2 lines, cathode on the right. Unfortunately, this is a very simple example. They're not all that simple. Now it turns out that with line notation, it fell into place in this example, but the electrodes, those metal bars that sit inside of the compartments, the electrodes must be the first thing written and the last thing written. So the electrode in the anode has to be written first, the electrode in the cathode has to be written last. And that's what it's going to say down here. The electrodes are identified as the first and the last symbol. Now, I'm going to show you another example of this. And we'll see several examples of line notation over the next couple of days. This is strange, and we'll have to just see examples and get used to it.